students. This session we will be discussing about active site and mechanism of enzyme action. So active site is the site which is present in the enzyme where the substrate moves and binds and gets converted into product. This site is also called as catalytic site because it is involved in the catalysis of a particular substrate. So according to Oxton, he pointed out at least 3 minimal point of interaction which is required for enzyme and substrate catalysis. The 3 point of interaction will be governed by two requirements. One is geometric complementarity, the other one is electronic complementarity. The geometric complementarity includes the shape in which the enzyme and substrate complement each other, and the electronic complementarity, which deals with the charge complementarity between the enzyme and the substrate. So there should be 3 points of interaction in which two binding groups will be there. In the substrate, two binding groups, and in the enzyme also we will be having two binding groups. And in case of a substrate, reacting group will be present, and in case of the enzyme, catalytic group will be there. So the reaction will be, or the interaction will happen between the reacting group which is present on the substrate and the catalytic group which is present on the enzyme. And the two binding sites also will be interacting between substrate and enzyme, so that enzyme substrate complex will be formed. Oxton has proposed there should be a minimum of 3 points of interaction. Based on that theory, based on that interaction, two hypotheses has been proposed for the interaction between active site of the enzyme and the substrate. The first is Lopinki hypothesis, which was proposed by Emil Fischer in 1890. Emil Fischer has also stated the presence of complementary structures between enzyme and substrate will be exactly complement to each other, so that the substrate can directly fit into the enzyme's active site so as to proceed to form the enzyme substrate complex, thereby the product and the enzyme will be produced. Whereas in case of induced fit hypothesis, which is proposed by Coastland in 1958, in which the free enzyme will be present in the solution where the substrate tries to go and approach the enzyme, and the substrate will be rigid in nature, the enzyme will be floppy in nature. The enzyme will go and bound around the substrate according to the substrate complementarity structure. The enzyme will adjust itself and bound around the substrate so that the enzyme substrate complex will be formed. This conformational change will happen to the enzyme and not to the substrate. The substrate will be rigid in structure. So corresponding enzyme substrate complex formation lead to the production of product as well as the enzyme pack. So in this diagram, we can see the substrate which is ridged and has a specific structure which is coming closer to the enzyme. Now the enzyme structure is not complementary to the specific substrate. So enzyme is floppy, the enzyme is just going and wrapping around the substrate so as to form the complementary structure with respect to your substrate. So now the enzyme and substrate which are complement to each other will be binding and forming ES complex. Now the E and S will be producing product and the enzyme will be reverted back to the original conformation. So according to induced fit hypothesis, the substrate goes and approaches the enzyme. The enzyme will change its conformation according to the substrate conformation so as to form enzyme substrate complex. Then product and the enzyme will be produced. So the catalysis of enzyme requires the following criteria. Number one, the enzyme, like other catalysts, forms a transition state which is of lower energy with respect to the reactants. Though it is not exactly same phenomena, the binding enzyme with the substrate at a specific binding site to form ES complex through the formation of unstable transition state. This unstable transition state, if it is stabilized, automatically it will be converted to the substrate product and the enzyme. In the enzyme substrate complex, the reactant groups are held in a close proximity to each other and to the catalytic site of the enzyme. The catalyzed reaction can now take place via the formation of unstable transition state to give products. The product may still bind with the enzyme to form another stable intermediate enzyme product complex which exists before the liberation of the product. And when we check the energy profile, the activation energy for the uncatalyzed reaction will be more, and both in the catalyzed and uncatalyzed reaction, transition state will be obtained. This transition state energy requirement, which we call it as activation energy, that is more in case of uncatalyzed reaction, whereas it will be less in case of catalyzed reaction, which will be catalyzed by either enzyme and also the other catalysts. When compared to the enzyme and other catalysts, enzyme have controllably lower activation energy. So when we come to the enzyme unit, most of the times we'll be denoting the enzyme unit as IU or U. So international unit will be considered. According to international unit, the amount of enzyme causing loss of 1 micromole substrate per minute under specified condition, whereas the SI unit of enzyme activity, which is kettle, which is the amount of enzyme causing the loss of 1 mole of substrate per second under specified condition. So 1U is equal to 16.67 nanocatals. And we have catalytic efficiency, which is defined as the number of molecules of substrate converted to product per enzyme molecule per second, which is called as enzyme turnover number or KCAT. This will determine how many molecules of substrate can be bound to an enzyme molecule, especially one enzyme molecule where the number of binding site per molecule will be removed. And specific activity, this will be used in most of the times in the criteria of purity during the isolation and purification process of your enzyme. Specific activity is of an enzyme is the activity of an enzyme per mg of total protein, and it is expressed in micromole per minute per mg. The specific activity is equal to total activity divided by total amount of protein in mg. Thank you, students.